Hello everyone, welcome to today's tutorial. Today's topic is numerical estimation methods. We have already discussed in detail about maximum likelihood estimators. Now an important application of maximum likelihood. We will learn to estimate maximum likelihood estimation with optimization, several optimizations. One important thing to remember: to do optimizations in MATLAB and in R, first we need to define the log likelihood functions in local functions. Then we need to call these locally defined functions for maximization or minimization, precisely for optimization. Instead of using the book, I will use my notes today. I think the writing might not be very clear, but it will be easier for me to explain through. The maximum likelihood estimator is a solution of a set of equations obtained by evaluating the gradient of the log likelihood function at 0. For many of the examples considered in the previous chapters, a closed form solution is available. So first example here is just an example of Cauchy distribution, where y1 to yt are TIID realized values from Cauchy distribution, where the function is this. We have the function where function is y by pi multiplied to 1 by 1 plus yt minus theta square, and the log likelihood function is just taking a log of this minus log pi minus 1 by t, summation of log of 1 plus yt minus theta whole square. This is something we need to remember. The gradient, which equals 0, is 2 by t summation of yt minus theta divided by 1 plus yt minus theta whole square. So this is a nonlinear function for theta hat for which no analytical solution exists, and so numerical optimization of the algorithm must be used. To obtain a maximum likelihood estimator where no analytical solution is available, numerical optimization algorithms are used. These algorithms begin by assuming starting values for the unknown parameters and then proceeds iteratively until a convergence criteria is satisfied. And general form of kth iteration is theta k equals function of theta k minus 1, where the function is governed by the choice of the numerical algorithm. In any situation, we just need to remember two parameters, theta k and theta k minus 1, and when a convergence appears, theta k equals theta k minus 1. The convergence criteria will continue until the convergence where both of these parameters equalize happens. So let's have a look into Newton method. The gradient and Hessian in Newton method for the previous problem is summation of g by t is gradient and Hessian is summation of h by t. The first order Taylor series expansion of the gradient function around the true parameter vector theta naught. One thing to remember: the true parameter vector which we use to initialize our optimization mostly sometimes arbitrarily chosen, or there are some other steps that I will discuss later. So by expanding through the gradient through Taylor series, this is the equation, the first order Taylor series, where the gradient gt theta equals 0 in the first derivation by default, and this equals this because theta k and theta k minus 1 must converge in the convergence criteria. Now, and theta hat here is the estimated parameter. So when the parameter estimation happens, theta k and theta k minus 1 converges. the linear equation in theta hat is, we just simply take theta hat, which is the estimated parameter, is equal to theta naught minus the gradient divided by the Hessian. This is the linear equation that we can solve with OLS. Remember, a practical use is maximum likelihood estimators as a function of unknown parameter 6 to estimate theta naught. This suggests that, however, that a natural way to proceed to replace theta naught happens with a starting value and an updating scheme. This is the basis of Newton method. So Newton-Raphson is when theta k replaces unknown parameters at kth iteration. And just having a look into it, here where the gradient is gk and the gradient and the Hessian including them, this is the iteration that will continue until convergence happens, and that convergence will happen when both of them equalizes at 0, and the only satisfaction, only way to satisfy the Newton-Raphson process, or again repeatingly, it converges when this particular equation, the estimate of parameter, looking into it, when we need this to be 0. So basically, if the second portion where gradient divided by Hessian is there turns to 0, then the estimated parameter equals to the initialized parameter. That is the motivation basically behind the algorithm. So this is where the satisfaction criteria happens. An example is exponential distribution that we will do later, where we use some initial values. There are y values we pass in, then this is the function where 1 by theta exponential of minus yt by theta is there, in which theta is greater than 0. And this is the log likelihood function. I'm just showing how I did the calculated to solve the log likelihood function. The log likelihood function is minus log theta minus 2 by theta. So this is the regular exponential distribution function. Minus log theta minus 2 by theta is the log likelihood function, where we have gradient, which is minus 1 by theta plus 2 by theta square, is just taking the first difference of the log likelihood function, and then we have the Hessian taking the second difference of the log likelihood function, 1 by theta square minus 4 by theta cube. Now we set the gradient of the parameter 0 for analytical solutions. Because it's 0, we know gradient is 0, first difference. When we set that to 0, we can easily solve our problem, which is finding the value of theta hat. Now generally we start the algorithm with theta naught equals 1, and the starting values for the gradient and Hessian in that case becomes g naught and h naught. As theta naught is not equals theta 1, as we can see from both of the solutions, this is not equals this, so iteration will continue until respectively theta naught almost equalizes theta 1, and the updated value is found in theta 2. So theta 1 1.33. again we pass this in gradient and Hessian, we do these calculations, and we find theta 2 equals 1.667. So this will continue, is gradient of 1 is less than gradient of naught. The algorithm is converging to converging in the convergence criteria. The calculation for successful iteration are reported here. So it will basically continue, as we can see, until convergence happens. So this is a basic example of this basic example of how maximum likelihood estimators work. Now we can solve this problem with information matrix, which is known this process. When we use information matrix process, we call it method of scoring. Information matrix is simply negative Hessian, nothing else. So it is simply negative Hessian. Here it is negative Hessian minus E H naught. So there is a little change in the process by replacing the sample average and estimate of by the sample average, an estimate of information matrix is negative of the Hessian, which is used in the Newton-Raphson algorithm, and we simply replace information negative Hessian with information matrix for our calculation process. And in case and the iterative scheme for the method of scoring becomes, the iterative scheme for method of scoring is theta k equals theta k minus 1, theta 1 equals theta naught plus g naught by I naught. This is the iterative scheme of the maximum likelihood of the Newton scoring algorithm. This is the so this term theta 1 equals theta naught plus g naught by I naught. So theta k equals theta k minus 1 plus g k minus 1 divided by I k minus 1. Okay. Then comes there is an example we are showing here. Basically, because we are using negative Hessian, so negative by negative becomes positive, gk minus 1 by ik minus 1. Otherwise it was negative, as we know. Just taking things from right hand side to left hand side, this is remained with a negative portion, but that is not true, because this negative becomes positive when we are using information matrix. That is what is shown here, and then a practice is shown. BHHH algorithm. BHHH algorithm stands for Bernd, Hall and Hausmann, 1974. This algorithm uses information matrix in the equations to express the information matrix as I theta is equal to j theta. J theta is the outer product, is simply the outer product of the gradients matrices. So this is simply the, we know about inner product and outer product, just the simple outer product of the gradients matrix. So the BHHH algorithm or BH3 algorithm is obtained by replacing the negative Hessian in equation by j. The negative Hessian is replaced by j evaluated at theta k minus 1, theta k minus 1. So we are just replacing the negative Hessian with j in BH3 algorithm, where we have the value of jk, which equals simply, jk is simply 1 by t, j theta naught is simply 1 by t summation of the outer product of the gradients matrix. Very important, highly used, continuously used in all the later chapters. So we apply this on a exponential distribution, and what do we find? Gradient for an exponential distribution is 1 minus 1 by theta plus yt by theta square, and part of the gradients matrix, outer part of the gradients matrix is simply, calculate that, very simple. Then use theta naught as equals 1 for initialization. When we use theta naught equals 1, then we solve this again, j naught, we solve this again, and with theta 1 the gradient vector evaluated at theta 1 naught equals 1. The gradient vector itself just in theta naught equals 1 is 1, where the Well, J naught is 2.1667, 2.1667 J naught. Well, when you solve this, you'll see that 2.1667 and 1. The updated parameter value is computed using, so this is the updating phase where theta naught is equal to theta 1 plus G naught by J naught, 1.4615. The remaining iterations are contained in the following blocks. Algorithm will in this problem, the algorithm has not converged even at 7 iterations, where the 7th iteration theta 7 is 1.8178. It is also apparent that successive values of the log likelihood function at each iteration do not increase monotonically. For iterations k equals 2, the log likelihood function's value was minus 1.69. For 1 k is equal to 3, the log likelihood function, instead of increasing, decreased to minus 1.403. So this is just a classical problem with this showing that iteration continue for a long time. The BHHH algorithm only requires the computation of the gradient of the log likelihood function and is therefore relatively easy to implement. A potential advantage of this algorithm is that the outer product of the gradients matrix is always guaranteed to be positive semi-definite. They are positive semi-definite. The cost of using this algorithm, however, is that it may require more iterations than either Newton-Raphson or scoring algorithms do, because information is lost due to the approximation of the information matrix. So Newton-Raphson, straightforward algorithm, then scoring algorithm where we are using information matrix instead of gradient and Hessian, and then negative Hessian is replaced in BH3, and that's just the updating scheme. These are the common changes. So what we are showing here is that in a BH3 algorithm, the benefit is that the matrix, the gradient matrix, is positive semi-definite, which is very important, and we always get that where given T by K matrix and K by 1 T by 1 vector, the BH3 algorithm can be written for a vector algorithm can be written as theta k equals theta k minus 1, and I urge you to concentrate here, equals x prime k minus 1 multiplied to x prime k minus 1 multiplied to y divided by t divided by x prime k minus 1 into x k minus 1 divided by t, and fixing them we have simply theta k equals theta k minus 1 plus x prime k minus 1 multiplied to y divided by x prime k minus 1 multiplied to x k minus 1. Now fun part, if you look into this equation, you see the second term itself is OLS and nothing but a simple least square regression, where the dependent variable y is regressed on the explanatory variable given by the matrix of gradients xk minus 1 evaluated at theta k minus 1. A comparative example, if you're looking into for scoring, we just have to look into Cauchy distribution. Just have a comparative example is so in this comparative example we are just simply going to compare a Cauchy distribution with an exponential distribution. A Cauchy distribution, the log likelihood function is minus log pi minus 1 by t summation of log 1 plus yt minus theta square. So just taking the mean, and then we have defined the gradient, the Hessian, the outer product of the gradients matrix, or we can simply call it OPG, and the information matrix. And then updating happens with theta 1 equals theta naught minus simply gk by in case of Newton-Raphson is G by H. In case of scoring, theta 1 equals theta naught plus, because minus becomes plus. We are simply using OPG for scoring, nothing else, very simple, just OPG. And for BH3 algorithm, theta 1 equals theta naught plus what we are using is gradient divided by, so we have gradient 1 by t, because this crosses out, divided by gradient multiplied to gradient transpose, or simply the OPG. OPG equals gradient multiplied to gradient transpose. So summation of gradient divided by gradient multiplied to gradient transpose, as we can see from here. Okay, then an example where we will use this for Weibull distribution. We'll do a Weibull distribution. A Weibull distribution looks like this, which is a nonlinear equation, alpha beta y to the power beta minus 1 exponential of minus alpha y to the power beta. And the log likelihood function, again I'm saying it again and again that in a local function I have to define the log likelihood function. The log likelihood function is simply taking log, very simple, alpha beta minus 1, this part, minus alpha 1 by t summation of, so simply you just take log this plus beta minus 1 multiplied to 1 by t summation of yt multiplied to summation of yt, minus, because this is exponential, we are taking alpha to the front out, multiplied to 1 by t, taking the mean, indeed, because we are bringing in summation sign, so bringing in summation sign, yt to the power beta, that's all. And then we have the gradient here, where the first term is the mean, second term is the variance, as you can see, very simple. So the gradient, the Hessian, we just need to remember these matrices, because we will simply have to abide by these structure whenever we are going to do the solutions. Okay, then comes only the iteration of Newton-Raphson and BH3 algorithm are presented here, because the information matrix, given the complicated structure, the information matrix is intractable, because we cannot track the information matrix. So we can only solve this problem with Newton-Raphson and the BH3 algorithm. Then comes Quasi-Newton method. A distinguishing feature of the Newton-Raphson algorithm is that it computes the Hessian directly. An alternative approach is to build up an estimate of the Hessian at each iteration, starting from an initial estimate known to be negative definite, usually the negative of the identity matrix. This type of algorithm is Quasi-Newton algorithm. The general form for the updating sequence of the Quasi-Newton algorithm, which is building on Hessian, is this: hk equals hk minus 1 plus uk minus 1. Hk obviously is the estimate of Hessian at kth iteration. Quasi-Newton algorithms differ only in their choice of the update matrix, nothing else. We are updating the Hessian instead of the parameter itself. One of the more important variants in Broyden, Fletcher, Goldfarb and Shamo. Okay, Broyden, Fletcher, Goldfarb and Shano. And Shano, in short, BHHH algorithm is the updating matrix that was used was uk minus 1, and this is how it looks. We'll probably not use it. This is just an example that another updating matrix was used. BFG in the case when all terms are scalars. In the case when they're all scalars, the updating matrix of BFGS scheme looks like this, and the approximation of Hessian is looking like this. That's all. Okay, we'll see an example where BHHH is used on exponential distribution. So given initial value to be 1.5, the gradient is 1 by 1.5 plus 2 by 1.5 square. Just the simple structure of exponential distribution gradient. The update parameter is, as you know, okay, that is done. The gradients evaluated at theta 1 is this, because now we are using the updated parameter and checking that in G3, the G theta. Okay, and taking the difference of theta is 0.722. Well, the gradient difference is minus 0.125. The updated value of the Hessian here is G1 minus G0 divided by theta 1 minus theta 0. Okay, very beautiful. So that for iteration k equals 2, theta 2 equals theta 1 minus G1 by H1. So because we have already found H1 and theta 1, we can also G1, we can also find theta 2, and this is how the iteration will go on. The algorithm converges at theta hat equals 2 in this process. In this example. Line searching. One problem with simple updating scheme is that updated parameter estimates are not guaranteed to improve the log likelihood function. As we have seen, log likelihood function sometimes falls as well. To ensure the log likelihood function increases at each iteration, the algorithm is now augmented by a parameter lambda. Okay, now this is going to be more interesting. We have to remember that the control, we are controlling the update parameter at each step with the introduction of lambda here. For lambda equals 1, the full step is taken, because when lambda is equals 1, it converges to the previous method. For smaller values of lambda, updating is not based on the full step. So the simplest way to choose lambda is to perform a coarse grid search over possible values for lambda, known as squeezing. So squeezing is, instead of using lambda equals 1, whenever we are using lambda equals half or lambda equals 1 by 4 or something like that. Alright, so an example where BH3 is used with squeezing. BH3 is used with squeezing, is from convergence problem. So here you see, instead of using 1, we are squeezing it with half. Why? Because in the problem that we are talking about, for simple BH3 algorithm, at iteration k equals 3, the theta value changes from 2.2512 to theta 2 turns to theta 3, where it becomes 12161, with the value of the log likelihood function falling. So instead of increasing, we are expecting log likelihood function values to increase. So in case if log likelihood function with each iteration their value falls, like for this problem, minus 1.69 to minus 1.84, we just mentioned that in a few minutes earlier, we need to squeeze the step interval with half, and when we do that at k equals 3 iteration, theta 3 becomes we get 1.7335, and we evaluate the log likelihood function at this new value for theta 3. The log likelihood function, instead of jumping down from 1.69 to 1.8, we find is jumping down to 1.7. So there's an improvement, but it is still lower. It's supposed to be higher than 1.69. For a log likelihood function from iteration 2 is still higher compared to log likelihood function's value in iteration 3. So we use lambda equals 1 by 3. the updated value is 1.9061, which is a very good increase from log likelihood functions value 1.69 in step 2 in iteration 2. So you see, using this we have minus 1.69. So the log likelihood value is minus 1. Log likelihood functions value is minus 1.6943. So minus 1.6999 minus 1.6943. It is still low, or no, it is higher than the log likelihood function evaluated at the second step. So you see, great. With squeezing, we have increased the quality, improved our algorithm, and we can simply go on and we will accept the theta parameter at convergence. Okay. So this was line searching. Next is the discussion of standard errors, and very important, computing standard errors. An asymptotic distribution of maximum likelihood estimator is with t theta hat minus theta naught turns to mean 0, and the variance is basically negative of inverse of information matrix. So the asymptotic covariance matrix of the maximum likelihood estimator is estimated by replacing theta naught by the estimated parameter. So replace theta naught by estimated parameter and invert the information matrix. You get the covariance omega hat, which is the asymptotic covariance matrix. So simply the estimated information matrix, the inverse of that is the omega hat, which is the asymptotic covariance matrix, or you see inverse of negative Hessian, also inverse of negative Hessian with estimated parameter is also omega the covariance matrix. So basically this is the covariance matrix. A popular alternative is OPG, and OPG is simply inverse of the outer part of gradients matrix theta naught. So covariance of theta hat parameter is simply the covariance matrix taking the average of the estimated covariance matrix. That's all. Exponential distribution of standard errors. Exponential distribution standard errors. So we have exponential distribution and we can simplify standard errors. This is how it is shown. Basically, simply we take the omega hat divided by t, and we know what omega hat is. Inverse information matrix estimated with the estimated parameter theta hat, not theta naught. No theta naught theta hat, or inverse of Hessian with the estimated parameter, or inverse of the inverse of negative Hessian, or inverse of the OPG. This is all omega hat, and we divide that by t. That's all. So there is a problem where we solve for grid searching. We'll do this problem later. Then comes standard error with nonlinear function. Okay, these are all. Now here I am presenting some of the regressions that we have used earlier, like time invariant, where the exponential distribution, this is important, yt square by 2 sigma square. For linear regression is yt minus beta xt whole square divided by 2 sigma square. 2 sigma square remains same everything. Time invariant is simply yt square. Linear regression yt minus beta x whole square. For autoregressive yt minus rho multiplied to yt minus 1 whole square. So in changing beta xt, we are just putting rho yt minus 1 whole square divided by sigma square. Bilinear time series model in place of beta xt. So in time invariant there was no beta xt. In linear time series we have bit xt. In autoregressive model we have rho yt minus 1. This is just the in the right hand side of the equation we're talking about, that is taken to the left, rendering the right hand side to be 0. Yt minus ut whole square is bilinear and autoregressive with heteroscedasticity, is basically also the same, nothing else, just the variance changes because the variance is heteroscedastic. So in a regular autoregressive model the variance remains constant, while the variance is a vector in a heteroscedasticity with with heteroscedasticity. And in a arch model it's a bit different, because now the game is in the denominator. So we have alpha naught plus alpha 1, the whole equation comes in the denominator. On the numerator we have yt minus beta xt, alpha naught plus alpha 1, yt minus 1 minus beta xt minus 1, so lag of these. So alpha naught plus alpha 1 multiplied to the lag of the numerator whole square. So why did I list these things? Because very simple, if we're trying to solve problems in maximum likelihood estimation technique, we have to have the log likelihood function. No matter what method we're using, we have to produce local function where we will pass in the log likelihood function, the equations of the log likelihood function derived from these equations, so that we can just pass it on to the main body of the function of our code, so that it can generate the do the optimization. So this is essential, very important to remember in the process when we are finding standard errors of nonlinear functions. There are two log likelihood functions we must estimate. So basically there are two functions, local functions we create. One is unconstrained and one is a constrained log likelihood function. What is the difference between unconstrained and constrained? In an unconstrained situation, theta is full, as I said, theta naught equals 1, and in a constant situation psi equals theta square, which replaces theta. So we take root over psi instead of theta. So and psi is simply theta square, so we take the root of psi. That is the constrained log likelihood function. This is called substitution method. So simply then we proceed with first and second derivatives, and then we replace everything of theta with psi, and the information matrix changes 1 by 4 sigma naught square theta naught square, replacing back again, and the standard error becomes of psi. Standard error of psi equals root over inverse information matrix mean, or root over 4 sigma naught square theta hat square divided by t. This is a substitution method for standard errors. It gives us standard errors. So we can then simply find standard error of theta with this. Another process is delta method, where theta hat equals y bar is sigma naught by t. The variance is sigma square mean, so that c theta is equal to theta square d theta to theta d theta naught to theta naught. We don't do this, we generally use the previous method. Concentrating, another one thing, concentrating the likelihood for certain problems. The dimension of the parameter vector to the estimated may be reduced. Such a reduction is known as concentrating the log likelihood function. So we're trying to control the dimension of the log likelihood function. So you have theta, two parameters, dimension is k1 for theta 1, dimension is k2 for theta 2. We do the first order conditions, which is a nonlinear system, k1 plus k2 equations and k1 plus k2 unknowns. We most probably write theta 2 hat equals d theta 1 hat. Then the problem is reduced to k1 dimensional problem. Very simple, because this was k1, this was k2, but this k2 equals gradient of k1, we have basically concentrated the situation, we have controlled the situation just introducing the gradient on the first parameter. Dimension has been controlled. So this is concentration of dimension. The log likelihood function is then maximized with respect to theta 1 to yield theta 1 hat parameter. Once the algorithm converges to theta 1, it substitutes back. We just simply apply gradient to find theta 2 instead of using a convergence criteria. So there's an example with Weibull distribution. We are already familiar with how Weibull looks like. Parameters are theta alpha b, the first order conditions with 0. We find this, and the two nonlinear equations are alpha hat, beta hat parameters. The first equation is giving us alpha hat equals t by root over y to the power b, which is used to substitute for alpha hat in the equation for beta hat. That's all. Some of the ways to select starting values: we can do arbitrary choice. There are consistent estimators that we can use. We can use restricted model, and historical values can be used. So basically we use arbitrary choice. Even some cases, remember theta naught is never 0. We always start with 1 or any arbitrary value. We will still get our expected optimized value, so no worries. A very common tolerance level that is applied is 0.0001. We have to remember that. And some of the more commonly adopted convergence criteria is objective function, gradient, parameter values, updating function. We know these things already. So let's start exercises very quickly. This was a very small chapter, so it will not take time. So we have a regression model, which is x is an explanatory variable with the given values, and then we need to simulate t equals 5 observation using the parameter values that is given to us, or the initial values. Basically we need to compute log likelihood function for given beta hats, and okay, again we have the vector given to us and variance. We have the parameter given to us again and variance, and we need to plot. Then compute log likelihood function LT0 for again some new here the parameter beta is a scalar where we have heteroscedastic situation. We have variances, vector of variances again. So let's see how it looks in MATLAB and in R. Whenever we're looking into maximum likelihood estimation algorithms, the first thing to look for is if there is any local functions. So as we can see from our first problem, there is no local function, but it will eventually come. But there are some in these simulations, because number A suggests us to simulate. As we have already seen, we simply do random state. This is the global stream. We need to load the compatibility requirement and set seed, and the kind is Mersenne twister, and then we are simulating model. After passing in this command set seed 1 2 3 1 2 3 remains same, so that we can get repeated same simulations. Passing in the given numbers, beta naught is 1, beta sigma squared is 4. We already know that from our equations given problem. Basically t is the length of x, basically where it is the size of x by rows, how many x observation you have by rows. And this can be easily, generally in MATLAB, length mean whenever we pass length, it takes the highest dimension. Now here size x1 means it is taking the columns. Remember, with size function, interestingly, the first number 1 is column, not rows. If we're passing 2, then it will look for the size of the rows. And then the general equation, which we have already discussed, beta xt plus ut. So beta xt plus square root of sigma square. Passing in the equation, we're grid searching on gradient with the given sigma value. Now the second problem was where here we're referring to this problem where given there are beta values are given and sigma square is 4. Okay, so sigma square given are the y's and sigma square is 4. What they did is that they generated a beta from 0.5 to 1.5 exactly. So sequence 0.5 to 1.5 at 0.1, and then a loop function. First you need to pass in a command to store the output of your loop, g1, zeros, 11 rows, 1 column, where it is this in R it is suggesting replicate zeros for the length of beta. Much easier, yeah. Instead of passing it, we could have done like that, the zeros in brackets size of beta, comma, yeah, these are in columns, so column is 1, so comma 1, that's all. Replicate length of so then 1 to again length of sequence in sequence of beta, I in sequence of beta, so 1 to beta, 1 to size of beta. I know beta 1 could have been much better instead of 111. This could have been 1 to size of beta 1. You still get the same result, you see, instead of this. R did a good job here. 1 to 11. So mean of y beta ix divided by multiply okay, beta x multiplied to x divided by sigma square now comes in play, but I have already included in my notes and I suggested that will be of some use. See here, beta x square divided by 2 sigma square, that's all for this one. Beta I multiplied to x multiplied to we are finding the mean of it divided by sigma square for the gradient of the particular distribution. Okay, so this is the gradient equation. Sum of y beta I will rotate multiplied to x, so there is no element by element multiplication in R, but there is specific element by element multiplication in MATLAB. Somehow I hope R understands that I want the element by element multiplication here. Anyway, so it is taking the summation of this y minus beta x divided by sigma square, the regular one, and I think because the mean is not taken, it must be divided by t at some stage, because it has already been divided by t with the mean. That's all. And then we need to do the plot. We're doing subplot. Just have a look into the difference between the plot equation. I'm not gonna spell this out. Next stage is gradient search with sigma 3.5. This is also as before mentioned, no difference. Following, that's all. This is the code. Yeah. Keep looking at the graph, how to plot the graph. Subplot 1-to-1 means there will be two submatrices of plots, that's all. Plotting beta against g1 and beta against zeros of the length of beta. So here beta The primary one is against G1, plotted against G1. Then we did the expression of beta. We don't need the expression here basically, but here it has a bit of tweak in our where we can pass in the expression, so we are doing that. What's the problem? There's no problem if we do that. And we then add the second line. What we could do in MATLAB directly with that, add the second line manually. Graphing commands are much easier, in MATLAB compared to R. The problem we have just solved is problem number 2, max grade, where we did simulate t is equal to 5 observations. We derived the expression for a gradient with respect to beta, and we did grid search on beta given this, and we did repeat this number C with 3.5. We wanted to do max graph, instead of we did max grid. So let's have a look into max graph very quickly. Okay, we pass in the random generation code, set default stream, not set global stream, and the kind for R is Mersenne twister. Pass in the numbers again. Equation is same. See, beta x plus sigma square, beta x plus sigma square multiplied to t1 square root of sigma square sigma variance, beta x plus square root of the variance. This is very default structure, multiplied to x, which will the whole thing will give you residual. We're generating random numbers here. With that we are multiplying with the standard deviation, very simple, and that is giving us the residual. So instead of RNDN for random number generation, we're using R norm for random number generation. T rows, 1 column. We don't need to pass in how many columns you need. It will automatically generate that somehow. And then sigma square equals, plotting with sigma square equals 4, as we have already seen in the problem. You see, information is already given to us. We're going to simply apply that. Again, we should have been used the length of beta, number of columns, rows that are in beta, instead of doing 21 by 1. So replicating 0 for the length of beta, and length of beta is, good job, they fix it near. The length of beta is simply, or size of beta 1 is sequence of beta, y minus beta x divided by sigma square, y minus beta x divided by sigma y minus beta x divided by sigma square. This is what this is, y minus beta x divided by sigma square multiplied to the mean, half basically. And then comes the log likelihood function, isn't it? Yeah, the log likelihood function is simply half log twice y minus half log sigma square minus half mean of z square. Very simple. Y minus beta x divided by sigma square. This is the tweaking part where we have the third bracket in I. And then for log likelihood function, it's very simple. Log twice pi. There is no tweak in here, there is no tweak in here, nowhere is any more tweaks remaining, yeah, except for in R we don't do element by element, and we did element by element in MATLAB. Makes things a bit difficult sometimes, but yeah, this is the correct way to do. I appreciate MATLAB's element by element operational support. Okay, then we create another subplot. We need 4 by 2 by 2 means 2 multiplied to 2, and the position is 1, so we have actually 4 here because we have 4 information. X axis is I, y axis is I, par mf row, just remember that. Plotting beta a1, type is linear. Expression of beta, pasting log lt, this log of lt multiplied to this. Alright, just remember that. Ylim we could zoom in MATLAB minimally, but yeah, we just want to look into minus 5.5 to 1.5. Then with 3.5 the equation remains same. There is no change in the equation with 3.5. Everything remains same. Paste. Okay, let's just read it out loud. What is within paste? Paste in inverted first inverted comma you have log L. Then there comes a second inverted comma, begins with t and a multiplication sign. Second inverted comma ends, and the first inverted comma ends, then comma, then again we have a first inverted comma, then you start a bracket within which you do a second inverted comma, which is nothing, just for space, then comma, then beta. There is no beta, is not in any inverted commas because we want the raw beta value, comma, then another space. This is just for space, another inverted comma. We're ending the bracket, then another inverted comma, because after previous input we put a comma, so we complete that bracket, and then we complete the bracket for paste, and paste is put in under expression. Kind of like a long road, but it's okay. Okay, for subplot 2 to 2, log likelihood beta remains 1, and the variances change. Everything remains as it is. So in all cases, just the variances are changing, nothing else. Sigma square f. So there is nothing else to explain here. Let's look into the next problem. Maximum likelihood estimation using Newton-Raphson. So max NR. Consider the regression model set out in example 1. Simulate the model for t equals 5 observations using parameter values theta naught equals beta 1, sigma square equals 4. Find the log likelihood function, the gradient and the Hessian. Evaluate the log likelihood function, the gradient and the Hessian with initial parameters 1, 4, that is mentioned in A. Update the values. So it is actually suggesting us what to do step by step. Continue iteration until convergence. Compare these values to those obtained from maximum likelihood estimators. This is OLS estimation, and this is sigma square. Just compare maximum likelihood estimation with the regular ones. So max NR, let's see what's suggested in max NR. Again, now this time there should be, there is still no local function created for this problem. Fine, it is easier for us. So this is random number generation. No, it was not necessary to twist it. They could have done it in the same way, but again, it's fine. Helper functions. Wrapper function to calculate inverse of a given matrix. See, okay, so you see in R they have generated a function for the inverse of a given matrix. Probably in R we don't have a specific inverse function. So basically I'm creating function of M which returns solve, that solves M. Let's see what solve is. Solve a system of equations. This generic function solves the equation for x equal bit over b can be the vector and matrix. Solve a b. So basically it's a solve function. Then solve the equation a multiplied to x equals beta for x. So b can be either answer matrix. So we are creating an inverse function with the solver, introducing the solver. That's it. Because you can have a look. This issue double which might not be available on all platforms. QR decomposition. Okay, so we are passing the inverse function here, and then we will start our regular problem. First, simulate the model. Beta x square root of random number generation remains same. Evaluate gradient and Hessian. Sorry, gradient and Hessian where beta given 1, sigma square 4, theta hat is equal to beta naught and sigma square. Both is theta hat, that is what is passed here. Not or, is just and. We'll still have a look. Yeah, where is the line thing? Okay, then comes the gradient. First pass, because you have two parameters, replicate 0 twice. Then 1 is, there is no for loop, but this is good practice anyway. Beta not x multiplied to x divided sigma square, and log likelihood function, that's all. Then h is equal to 0s to 2 Hessian. What I'm trying to do here is that I'm trying to create a matrix where in the gradient we have 2 rows 1 column, we have 2 rows, h is Hessian, which is a k by k matrix. We have 2 rows and 2 columns, and here we are filling everything up, you know, manually, by storing in one gradient matrix, which is n by k, 2 rows, n equals 2 rows, k equals it's n by k, and it's k by k, which is a square matrix. So summation of x square divided by sigma square, then beta x for h12 and h21 gives you the same result, and h22. So h11 you have the mean, and h22 you have the log likelihood function generated for you. Just have a look. See, this is what we are doing, where in the first we have the equation solved, then the log likelihood function for gradient, for Hessian minus 1 by sigma squared the mean, and the log likelihood function into 2, but these two remains the same. That's what we have done. In case of OPG it will be a bit different. So the problem is located in number 27, page 27. So that's it. We need to remember this. This is quite simple. X square divided by sigma square. Yet sometimes might make mistake with that. Then average log likelihood at theta naught is simply log of twice prime and log of sigma square, then mean of this equation, that's all. Instead of sum, we are doing mean of this equation and mean of this equation, you see. So this is average log likelihood at theta naught. Then Newton-Raphson update manually, theta 1 equals theta naught minus in g by h. See, inverse of h multiplied to g directly. In R we need to put the multiplication sign between two percentage signs. Beta 1 is equal to theta 1 the first element of theta 1, sigma square is the second element of theta 1. Alright, have we defined theta 1 anywhere? I guess, okay, it might not be necessary. Newton-Raphson update, because h and g divided by h reduces the dimension of the matrix that is under discussion. So dimension control, very important, we have studied today. Concentrating the likelihood, where we see if we theta 2, the second parameter, if we put that in the first parameter with a gradient, it reduces the dimension, or simply divide theta 1 hat divided with theta 2 hat. Alright, so we are controlling the dimension. How? We are simply, where is it? Yeah, this is Newton-Raphson update, because we are simply dividing with the gradient. You see, the Hessian is being divided with the gradient. Dimension is being controlled. Out from 4 we are getting 2. Always remember, in all problems dimension is important, and when lower dimension is on numerator and the higher dimension is on denominator, after division we get the lower dimension, and we control the dimension without losing of any information when we pass that information in the gradient. That's all. Again, average log likelihood at theta 1, so this is theta naught. Log likelihood at theta 1, is there any change? Yes, there is a change, because we have sigma square 1 and beta 1. We don't, yeah, we have passed both beta 1 and sigma square 1 instead of beta 2 and sigma square 2, and then so we just print that. Very simple, easy, and very interesting updating scheme without any function iterations. Great. Another way to address the same problem is with iteration, and I'm not gonna go into details. You have already seen these, how to do these. You know, we have to first create the Hessian and gradient at theta 1, evaluate that, find the average, and then comes the interesting part where we have Newton-Raphson, and this will continue, the iteration will continue until 0.001 is reached. So everything, all the iterations will continue until you reach from 0 until 0 the tolerance level is exceeded. So you see, up until the gradient and its inverse is 0.001, it will continue. Very simple. So again we pass in everything. Okay, this is the point of making functions. We're making a function. We pass in theta, beta is the first element of theta, sigma square is the second element of theta, theta equals theta. You see, there is no theta naught or theta 1, there is just theta, and in theta we are passing in theta's value that we have already calculated. In theta we have beta and sigma square, we have already passed those in. Then we do gradient again. Okay, there is no change to this gradient compared to the previous calculation of gradient, and Hessian remains same. Is what's changing here in Newton-Raphson. Newton-Raphson taking it sorry, R is making it even easier, where the tolerance is set for 0.001. We could have done that, while the tolerance of the gradient, no sorry, though the transpose of the gradient multiplied to the gradient is greater than, up until that point there is no change in their functions, in their iterative functions remains exactly the same. Inverse multiplied to g for theta 1 is the element, because it's the element we're talking about, so it's in the third bracket, second element in the third bracket. Zeros, 2 rows 1 column. So C bind, column bind, not row bind, column bind, repeating zeros in the 2 rows and in the 2 rows, that's all. Column bind. So here it is the same, there's no change. H is first, where 2 rows 2 columns of square matrix is being created. These are the tweaks of R and MATLAB. See, now we need to create a matrix manually. So we want zeros in all elements, then we want the column, the concatenation of 2 by 2, concatenation of 2 by 2 arrays, where everything will be 0, number of rows are 2, number of columns are 2, and that is passed in a matrix. You have a square matrix. Long sentence. In G we are doing column bind for just 2 by 1 vector, that's all. There you go. Then optimum average likelihood function A1 with the calculated sigma square and beta, and then we just represent it, that's all. So with iteration it's a bit different. It was easier with no iterations, but iterations is something that we cannot avoid in most cases. The fourth problem, exponential distribution. The aim of this exercise is to reproduce the convergence properties of the different algorithms. Suppose the following observations are 3.5, 1 and 1.5. We are in page 28. Let's see what's the different algorithm in table 3.1. There is a table 3.1, right? Okay, so estimated stationary gamma distribution. Oh no, we're talking about a table, not a figure. Alright, let's see. This table 3.1, where theta k minus 1, gk minus 1, mk minus 1, log k minus 1, theta k, all these are estimated with Newton-Raphson scoring and BH3. Okay, so we're just gonna do that. This was page what? 6, and we're going back to 27. Derive the log likelihood functions using theta 1 equals 1 the full information, then 1.5 as the starting value. Let's see what happens. Max exp is gonna be easy. Alright, program to estimate exponential model. Let's see if they have created any local function. No. Okay, let's start. First we are doing the simulation, inverse wrapper function. So there are 10 iterations that we will require exactly the same. First with Newton-Raphson, we start with theta 1 k for k equals 1 to number of iterations. When number of iteration is 10, so because just 10, we don't need to like create a storing array, it will automatically store. Row names is sequence to number of iteration. This is an additional tweak. Row names is equal number of iteration. Column names is gj log l theta k, gj log l theta k. G j log L g j log L theta k. Sequence, so g is equal to minus 1 by theta mean of y by theta square, Hessian 1 by theta square minus 2 by log theta minus mean of y by theta 1 by theta square minus 2 mean of y divided by theta cube. These are regular equations. So gradient is minus 1 by theta plus 2 by theta square when you have an exponential distribution in case of that, and Hessian is 1 by theta square minus 4 by theta cube. To mean y, or what we did is this, to mean theta cube, to mean y 1 minus theta by 1 by theta square, mean multiplied to y, mean y divided by theta square, mean y divided by theta square, to mean y divided by theta cube. Okay, so it's the same thing. We are creating a residual, well, array with the dimension c. Okay, what is res? I'm not sure. Passing something to res where I'm creating an array with the row names and the column names. So I'm still stuck in this. Length of row names, column is length of row names up until the length of row names. Row names and column names. Dimension is the list of row names and column names. So creating dimension, matrix as dimension, setting the matrix as dimension. That's all. Row names and column names, row names, column names, passing that to an array. Sequence up until number of iteration remains, the mathematics remains the same. Populate results table with values. So okay, under G we have G, with under J we have TG multiplied to J. Oh man, log L theta theta. Okay, we're just putting these in and making populate results table. We're just creating a results table, and we are rounding it up. That's all. Creating a results table. So this is results for k rows, number of k rows for all the k rows, G, then comes J, then come log L, then come theta k, so that we have kind of like that type of that we have just shown, that type of table. It will automatically be created in our great MATLAB. This is more difficult with this. Then scoring algorithm, theta is equal to 1, again I is equal to 1 by theta square, 1 divided by theta square, log L is equal to log theta minus mean, because in scoring we are interested with information matrix I. We don't need the Hessian here. Theta remains same, theta inverse multiplied to inverse of I, G multiplied to inverse of I, that's all. G multiplied to inverse of H, negative Hessian, positive information matrix, which is 1 by theta square. Again we are just we created a table here, theta with theta 1. So what is the table here? Dimension names. First property is dimension. Under dimension property we concatenate the length of the rows and the length of the columns accordingly. How are we getting the length of the rows and columns? Because we are already defining before, the rows are number of iteration, the columns are with the title. We are putting even the headers of the columns. Then the dimension names. Second comes the property. We turn on the property dimension names, which equals listing of row names and column names. We pass that all in under array, and we put that in results, and results become a table. How do you populate results? Simply push the elements in each rows or columns, like k. Who is k? Where I'm trying to say that there is k is just the sequence 1 2 3 4, so that it looks like number 6, page 6 looks like this. See, iteration k1 k2 k3 k4, it will show the iteration. That's all. Then comes BHH algorithm. With BHH algorithm, what's changing? I'm just getting the gradient, which is the mean of GT, and then outer product of the gradient I'm bringing in. See, mean of inverse of gradient multiplied to gradient, nothing else, and then I'm populating the results. Then with squeezing, theta equals 1 by theta square, mean, gradient, with theta, everything remains the same for squeezing. Theta hold is theta log hold, no, theta old is theta, log old is log L. Theta equals, again I'm doing it again, inverse of g theta, and in jg, this is all fine. Log L is minus log theta minus, this is all fine. Up until this is easy. If log L is greater than log old, so if log likelihood function increases, see, it is supposed to if log likelihood function falls, so if the value of log likelihood function, the current log likelihood function, with each iteration, what is supposed to happen? The log likelihood function values should be higher, not smaller. So if that happens, display full iteration step successful. Fine, that's good. If log likelihood display instead of display, we're just concatenate and display, we're using that function. But else, what we will do is full stop iteration step not successful. We want to make a stop, and then we start a for loop function for m2 to 10, because 1 is already passed in. The lambda value is 1 by m. Okay, I'll continue for, we will continue for, no, 2 to 10 is not 1, 1 by 1 is 1, so up until 10. Squeezing with step, concatenation, squeezing with step, and display, replicate and replicate this m minus 1. Theta is equal to theta old plus lambda inverse g and log L. Okay, in case if, then it will continue, for the for loop will continue if log L is, when log L is greater than log old, then we'll break it, otherwise it will continue until continue, then display. Populate result tables with values, no tweak in there, print. Then comes BHHH algorithm. It was interesting, no? So if it is greater than this, log L is greater than, the iteration is successful, so it ends. If not, then it will continue until we have a higher log L. Until we have it, then we will continue. Then BHHH algorithm, theta h, number of iterations are 9 given. For k is equal to 1 to number of iterations, everything is already given there. D theta, BHHH inverse of h, g by divided minus g by h, gold g equals minus 5, dg is delta g, so we're talking about delta g. As you can see, delta g is gk minus 1, theta k theta, g minus gold, see g had inside g we have this value minus 1 by theta, theta k. Very simple. The previous, nothing is different. With BHHH we just use the Hessian instead of theta, and h is h minus the whole equation. H is h minus the whole equation. This is the equation. Okay, h minus d theta into plus 1 plus d theta, h into d theta into dg transpose plus dg into d theta into h, d theta transpose into h, d theta into dg. Just have a look into the sequence. BHHH, this was pretty difficult, no? D theta minus theta log L. Up to this is fine. Then LD, are you doing LD gold? Yeah, h minus h into d theta into d dg transpose of dg plus dg into d theta transpose h divided by dg transpose by d theta plus 1 plus, so basically plus 1 plus delta theta d theta into d theta transpose h into d theta, h d theta into dg transpose, and d theta transpose dg transpose. So d theta transpose divided by dg transpose, the denominator remains same, numerator is changing, multiply to dg into dg divided by dg, again denominator remains same. Instead of memorizing, keep looking into this, dg del theta dg. So you see 1 plus del theta hk minus 1. That's all, just remember that. Okay, next comes the next problem, which is, again, let's go to, we have done exponential, then Cauchy distribution. Cauchy, let's see how the Cauchy is. Okay, the Cauchy, max Cauchy. To begin with, this is Cauchy distribution, as we already know, and the log likelihood function is minus log pi 1 by t log of 1 plus yt minus theta square. The gradient is 2 by t yt minus theta divided by 1 plus yt minus theta square, and the maximum likelihood estimated theta hat is just this. So this is the Cauchy. Let's have a look into Cauchy with R. So given are these values and theta naught equals 3, initializing inverse wrapper function has been passed for R. Newton-Raphson, gradient is 2 sum yt minus theta. Where am I getting it? From here, yt minus theta 1 plus yt minus theta whole square. And Hessian for Cauchy, are we familiar with Hessian? Or for Cauchy, so this is the Hessian for Cauchy distribution. So this is the Hessian h2 sum yt minus, we're just bringing that up here, 2 sum yt minus theta naught square minus 1 divided by 1 plus, and then Newton-Raphson, theta in Newton-Raphson is theta naught minus inverse of Hessian. So this is just theta naught minus this portion. Okay, theta naught minus inverse of gradient divided by inverse of Hessian. So we have already calculated Cauchy and just the difference. The method of scoring method. In scoring, the gradient we already know, I equals t by 2. Information matrix, and theta with scoring is plus inverse of information matrix. So for Cauchy, information matrix was half, as we can see. With scoring, very simple process. For BHHH algorithm, gradient remains the same, no tweaks in here actually, that's why I'm not going into detailed explanation. Theta naught and just plus inverse gt, that's all. Cauchy, for Cauchy, and that is basically all. It's a very simple, you just pass in the equations that you learned, that's all. We initialize, pass in Newton-Raphson, multiply gradient and Hessian with Newton-Raphson, that's all. Then I think the next problem is, this was page 9, Cauchy, and then comes Weibull distribution. Okay, for Weibull distribution we know the gradient, this is the equation where the log likelihood function looks like this. We have the gradient, I think we have already discussed slightly. We have the Hessian. So what happens in a Weibull distribution? In Weibull distribution, here, given the information, first time in Weibull we have local functions. Okay, so first define, always look into the local function. So function log likelihood function, and my inputs are theta and y. Okay, so I'm gonna be able to include theta and y, and theta 1 will be saved in A, theta 2 element, the second element will be in B. Then this is the log likelihood function, log y A into, then negative log likelihood mean, negative mean is log likelihood function. So concentrated and non-concentrated, I have discussed that earlier. Function theta y, this is also the same, just the elements inside is in third bracket, nothing else. Return f, so we need to finish our function with return, where in MATLAB we don't need to do that. Concentrated log likelihood function, function of by, y because it's concentrated, so y divided by mean of y multiplied to b, that is the concentration part. We have already seen that, but in case if we cannot remember, let's have a look. Right, concentrated alright, concentrated with big C. Okay, not necessary, concentrated is here, I know, just spare with me 1 second. There we have Weibull. Here we're talking about Weibull, and so there is concentrating the log likelihood. Oh, we have already discussed that, to control the dimension of concentration, parameter constraints. We're putting constraints and trying to control by putting in constraints. Okay, there you go, substitution, constraint and non-constraint. So first and second derivatives, this is constant, so you see psi root over psi, and we are putting constraint, we're concentrating, so no it's not constraint, it's concentrated, y by mean of yb. So we're just concentrating, we're just dividing, replacing to the left hand and right hand side. So theta 1 equals g theta naught, that's all, very simple. So after concentrating, we return the function again, lf, lnlc by, inputs are theta ay and where by. Transformed log likelihood function is theta y lnlt log b minus log b1 log a log b minus log 1. Oh, when we are using equals b and in place of b we are putting 1, so we are transforming. This is the question, this is given in the question, must be given in the question. Well, solution. So alpha 1 beta is equal to 2 from the Weibull distribution, alpha naught 1.5, alpha 1 beta is equal to 2. Alpha 0.5 beta is equal to 2, alpha 1 beta is equal to 2, alpha 1 beta is equal to 2. Is there any other thing given in this? Okay, just forget about that. Just remember, this is transformed where we are placing the value of a as 1. Oh, okay, alpha 1, right. Yeah, there you go, alpha equals 1. That's what it is being put in for transformation. We are constraining just one parameter, but we are finding out b because we are not interested to find a here, because we have concentrated a in this function. So when we include b, a will be automatically generated. Then we are transforming log likelihood function with for b only, and return gradient vector and alpha beta gradient g1 g2 on alpha mean of y. This is coming from just what we have discussed, we have shown you. Return Hessian matrix, C-bind Hessian matrix H11. So alpha theta, then okay, Hessian matrix function of theta alpha, the H11, H12, H21. Remember, H11 and H21 equals H12, they remain the same, and H22. These are all coming from here, you see, page 10. So we're just putting in things in here that are already mentioned for Hessian one. So this is the Hessian matrix. So basically we are returning each vector, gradient vector, Hessian matrix, that's all. OPG matrix, very simple, no tweaks or anything. And then we must be calling it. So what we have a log likelihood function. We have concentrated log likelihood function where we are finding a, we don't have value of a. We are transform log likelihood function where we are finding b, where we don't with L, we're finding b with given L, but we don't have a here. And then we are returning, and then now we are going to call the equation in the main code. So first random number generation, then generate Weibull random numbers. Alpha beta is given, use built-in function. Okay, to generate a Weibull random number there is a built-in function for Weibull. Let's see, r Weibull. We have a Weibull built-in function for Weibull distribution, where what is included in that. The beauty of R is that there is a lot of distributions already mentioned, so we're just gonna call the Weibull distribution where we have the shape vector, the shape is t, the scale is 1 by alpha, to the power 1 by beta, and the shape equals beta. So first x, we're talking about in R Weibull n is x, then comes shape, then comes scale, or we can just pass it scale equals 1. They use scale equals 1. We use the built-in Weibull function. For this we simply use 1 by alphas to the power 1 by beta. Why we use that? we are using that because we are following this non-normal distribution alpha y to the power beta. So we are doing 1 by alpha to the power 1 by beta, and the shape will be of beta. So if we just need to run that, and that will give us a beautiful Weibull distribution. We can manually generate Weibull number with x log 1 by z, or using MATLAB function Weibull random, generate Weibull random numbers with functions for in MATLAB too. So max Weibull, use built-in functions for Weibull. We are creating a function here, max Weibull. Okay, we are also creating a function here, max Weibull. So both are passed in functions. Everything goes within the function. So Weibull random, again 1 by alpha 1 by beta square. Beta is the, as we know, is the shape, and the size is t by 1. Going the other way around, fine. Then comes the starting values, theta naught, which is column bind of 0.5 1.5. Alpha is the first element of theta naught, beta is the second element, which is 0.5 and 1.5. That's all. 1 to t. Then gradient vector is theta naught y, Hessian matrix is theta naught y. Because we have already created these functions, and we say that we'll pass in theta naught, theta and y, we are calling those functions now. Very simple. Okay. And then we're just doing, and Newton-Raphson update, theta 1 is equal to theta naught minus inverse of h, because we have already calculated theta naught. Theta naught, we are just using 0.5 1.5 here, minus inverse. Update is simply this, estimate at iteration 1, display theta 1, display number to string log of L theta 1. This is coming from the function again, so they're teaching us how to draw functions. That's all. Okay. Then BHHH algorithm. For the BHHH algorithm, theta 1 equal theta naught. So we are just changing the algorithm. Solve GJ, solve. Okay, solver function, inverse instead of inverse, we are using solver function that we have called before. You see, solve. Yeah, we have called it before in somewhere, because inverse function is known as solve in here. Okay. Solve HG, inverse of H, fine. Then call to optimize the function. Now the optimization, theta equals if any noun, get theta log L theta y comma theta 1. So this is one part. This is at function, so at theta log L, I'm talking about the calling the log L function, and the other one is theta 1. Let's see, optim instead of just passing optimization, so just optim, call optim to optimize function, call if any noun to optimize function theta 1. See, theta 1, which is the last element, log L. We don't need to actually mention the whole line. Log L, R will understand automatically. Y equals Y, I'm not sure, let's see. General purpose optimization, par, initial values for the parameters to be optimized over at par. At par is the initial values. Initial values at par means if in a function to be minimized, a gradient function, a function to return the gradient for the BHHH model person. Method, the method to be used, lower bound, upper bound, control, Hessian. All right, fine. at par, initializing initial value theta 1 log L will happen up until y equals y, y equals y. I understand that function. Let's have a look into the function. What did we do in the function? Y is equal y theta y by theta y log L t. I think it's a way for R to call that, okay, I want this to optimize up until this happens. Okay, the method of BHHH at par. G is gradient vector, as we know. Call optimization to concentrated softim theta 1, the second element theta 1 second element log LC y equals a method BHHH at par. Just remember that. Concentrated likelihood second element, using the second element in concentrated likelihood. Standard error, we can use the delta method. We might not use the delta method. This is given in the equations, we already know it, so don't worry. Okay, so what else is there after this? Very tiring. Okay, finally, Lefty-Kurtis in distribution of asset returns. Okay, this would be interesting. Max returns. Okay, what's there? Let's see. The empirical distribution of asset returns tends to be Lefty-Kurtis because it exhibits fatter tails and a sharper peak. Fatter tails and a sharper peak than the normal distribution. To capture this feature, a student's t-distribution is often used to model the distribution of asset returns. The standardized student's t-distribution is given by this equation, where yt is the asset return, mu is the mean, sigma square is the variance, omega is the degrees of freedom, and tau is the gamma function. It's gamma, it's not tau, is capital Gamma is the gamma function. The data daily share prices of Apple and Ford from 2nd January 2001 to 6 August 2010, a total of 2,413 observations. Compute the daily percentage returns on Apple and Ford. For each asset return, compute sample statistics of the first 4 movements and plot the distribution. Estimate theta is equal to mu, sigma square, and omega by maximum likelihood for each asset return using the descriptive statistics as starting values for mu and sigma square, and choosing alternative starting values for omega greater than 2. Interpret the parameter results. Repeat for restrictions. This would be interesting. Let's see how they did it. Is there any function created? Yes, function created. So let's start with the functions first. That is the most interesting part. Created function in R. Must have. So there you go. Interesting. In R, the functions are generally created in the beginning, I see, and then the math is done. In MATLAB we don't do that. We do the functions at the end, then we call the functions. Okay, let's see. Function of L, where we are gonna input B and Z. M is B equals 1, S equals absolute value of the second term, MS, who are MS, so you see mu, S is the sigma, and omega is V. So by S we are meaning sigma and omega. S is a square, S2 is simply sigma square, then log gamma is the whole equation, gamma V plus 1, gamma log pi, the whole equation here is put in here. No, log of pi log gamma v by, oh, this is the log function. Do we have the log function for t distribution? No. Let me see. Do we have a log function? Constant in constraint. Let me see. Is that okay? So you just simply take log of that equation that is mentioned, and taking the log, we have the log distribution, then minus, okay, a normal distribution, log of L function bz m is as a mu sigma absolute value of b square, log normal probability density function, probability distribution function is zms minus, okay, so these two are created. Now let's call the functions. Whole thing is put into a function called max returns. Data is loaded, 2413 observations, then we are passing the information. So as matrix we are passing all 1 to t for apple and for fold. We are computing percentage returns in the same method. 100 to, we are selecting a return, compute the descriptive statistics, mean standard deviation z, skew and kurtosis. We are showing the results. Okay, fine. We are doing the figure histogram of z and up to 21. Now z breaks 21, color, probability mean, x lab. If you don't know these things, just keep them as they are. For x, sequence of mean z to maximum of x, curve, these two are new thing, minimum of z, maximum of x, in between by 0, 0, 1, curve is d, normal distribution x, mean equals mean z, sd equals mean is the mean of this, standard deviation of this at d. Estimate the model by maximum likelihood estimation is density distribution. We have already, this is the initialized value. We have already mentioned the distribution function. Optimal large scale of display iteration or display of, okay, CMS5. Estimation results, optimization, start, log L, z equals z, method Hessian. So initialize optim, we have already seen optim. What is there in optim? If you want to see one more time, just have a look. It is very simple. Par, initialize initial value, start initial value, then function, with the function is log L function, log likelihood function, then the gradient is z equals z, the gradient is z here. I'm saying, and the method is VFGS used, lower upper, not necessary, control, not necessary, Hessian is true or false, logical should numeric differentiation is returned, so either true or Hessian is false if you want the result for Hessian. So this is gradient. If I don't pass anything, it will be known as the gradient. And so estimate beta hat, initialized value will be stored in beta hat, initial value is stored in beta hat. Beta hat will be at par, beta hat will have the estimated results, estimated results, the value at value will be coming here, par is the parameters. Now I remember, is parameters is the log likelihood function values. A we don't need them, Hessian, because gradient is there somewhere. Hessian, we want the Hessian log likelihood function, then Vc is equal to 1 by t minus 1. This is the variance covariance omega matrix, 1 by inverse of Hessian. We already know it. So very interesting. You see the difference. Remember the difference. The difference is for MATLAB, what we are doing is that we are directly calling all of the functions with optimization. We are directly calling for all the solutions that we need. Here we are manually calling the function each time and asking the function to provide us with the information that we need, which is not bad. Okay, so this is really good. This is a new learning for me. With normal distribution, again, estimated results, optim start. For normal distribution, we're starting with the first two elements. We're calling for the log L1, ZZ method, Hessian, everything is remaining the same. We are starting with the first two elements here, and we started with the given as MS5, and we are starting here for normal distribution. We are starting with first two elements. Is there any elements given in the question? No, we are just taking what was there. We had mean, variance, and 5. 5 was mean, variance, and 5, whereas 5 was what? Okay, where am I? And omega, we had omega, mean, variance, and the degrees of freedom. Degrees of freedom 5. With student state distribution, here we don't need the degrees of freedom 5, so we just are calling for the first two elements of start. That's all. That is awesome, simple. And then column bind, print column bind. We'll just do this in columns, show them the results in column. Parameters which we had. Beautiful. Okay, so basically that is up to what I wanted to show you. I'm not gonna go into the rest. I'm not sure how important they are, and they're gonna take a lot of time. Thank you very much. We're completing chapter 3. I need to admit here that this is not, I'm not preparing this for public view. I'm preparing for my own preparation. So as the basic intent is not to teach this topic, as it deviates from that intention, you might find that it is quite difficult to follow sometimes if you are following this. And I'm also assuming the people who are watching this already are familiar with MATLAB, because I am, so I'm trying to understand or looking into MATLAB. That is my objective, as well as revising my econometrics. Anyway, thank you very much for your patience, and yeah, I think I'll keep coming with some new materials. Thank you.